In this lecture, I will discuss the dynamics of motion of objects. This is the first part of 2 lectures on the effect forces have on the motion of objects. In this lecture, I will discuss Newton's laws of motion and some of the specific forces that are associated with the mechanical motion of objects. First, let's define force. Force is simply defined as a push or a pull acting on an object. And you can associate that with your everyday activities by thinking about what actions do you do when you want to move an object. For example, you want to pick up your phone. What you're doing is you're applying force, and this force is a pulling force. You're pulling on the phone to pick it up. A pushing force is typically applied when you are moving an object away from you. For example, pushing a shopping cart or pushing a lawnmower or any other pushing motion. When force is applied to objects, that causes the object to move with acceleration. So here we will focus on Newton's 3 laws of motion. We are going to call this part of the course Newtonian mechanics, because Newton's laws describe how force affects the motion of objects. And Newtonian mechanics is valid for everyday situations. It is valid for speeds that are much smaller than the speed of light. Newtonian mechanics is not valid for speeds that are close to the speed of light. Newtonian mechanics is valid for objects with measurable size, such as everyday objects that we deal with in our life. However, it is not valid for objects that are on an atomic scale structure. So elementary particles do not obey Newtonian mechanics. However, for the purpose of illustration of certain concepts, we may look at the motion of some elementary particles in the context of how force simply affects their motion. And Newtonian mechanics is also viewed as an approximation of general relativity. Historically, before Newton postulated his Newtonian mechanics principles of how forces affect the motion of objects, it was thought that there was some influence necessary to keep a body moving, and that the natural state of objects was at rest. And this seemed a reasonable assumption due to the fact that friction exists, but the people then didn't know about what friction was, that it was a force. However, if you imagine a frictionless surface, such as the surface of a frozen lake, if an object, and you ignore the friction, if an object, let's say a hockey puck, is sliding across that surface, since there is no friction, this hockey puck will never slow down as it's moving on the surface. That means that if the lake was infinitely long, this hockey puck would be moving forever with a constant speed. So, in reality, we know that the hockey puck actually will slow down and eventually stop on the surface of the lake, and that is because force acts on it. And if you remember from the previous slide, I said that when force acts on an object, the object accelerates. So in this situation, the hockey puck is slowing down, so it decelerates. And so therefore, it experiences force, and that force is the force of friction. And so based on those observations, Newton formulated his first law, which states that if no force acts on a body, the body's velocity cannot change, which means that the body cannot accelerate. And so think about it in the context of the example that I just gave. If the hockey puck is moving on a frictionless surface, it's left on its own, it's moving with certain velocity, there is no reason for that hockey puck to change the direction of motion or to speed up or to slow down on its own. It will continue to move the same way forever unless an external force is applied to the puck to make it change the way it's moving. The unit in which force is measured is the Newton. And later we will see that 1 Newton is equal to 1 kilogram times meter per second squared. Another characteristic of force is that acceleration of a mass is proportional to the exerted force. And since force was defined as a push or a pull, which indicates direction, forces are vector quantities. So forces have magnitude and direction associated with them. This is extremely important to remember because manipulations of forces or calculation of problems which involve forces require to treat forces as vectors in order to get the correct answers. So all the rules and definitions that were stated in the chapter about vectors apply to forces. When we say net force, we mean that this is the vector sum of all forces that act on an object. So, all forces that act on an object are added as vectors, following the rules of vector addition, meaning in unit vector notation by components. And then the object will behave the same way as if that one net force was acting on it. Forces obey the principle of superposition, which says that a net force has the same impact as a single force with identical magnitude and direction as the sum of all forces acting on the object. And so then Newton's first law can be restated a little bit more precisely as if no net force acts on a body, the body's velocity cannot change, that is, the body cannot accelerate. This statement of the first law has a deep meaning. So I already talked about the moving object, and in the absence of net force, the object will be moving at constant velocity. However, this also applies to an object that is at rest. When an object is at rest, its velocity is zero, it's a constant. The object has no reason to start moving in any kind of way, acceleration or to turn, in the absence of net force. The only way this object will be moving is if there is external or non-zero net force acting on the object. And so the meaning of the first law is extremely important. Objects only change the way they move when there is net force acting on them. Otherwise, they do not. In the chapter about vectors, I stated that in order to be able to describe the position or the orientation of a vector quantity in space, we needed to introduce a reference frame or a coordinate system. Obviously, the same applies to forces since they are vector quantities. However, since forces are linked to accelerations, it is very important to make to differentiate between two different types of reference frames or coordinate systems. We can have a reference frame which is not accelerating. So it is either at rest or it's moving with constant velocity. And then there's other types of reference frames which are moving with some acceleration. Why is it important to differentiate between the two types of reference frames? Because Newton's laws, the first law, does not apply for reference frames that are moving with acceleration. So let's give an example. Consider you are sitting in a car that is moving, and then the car starts to make a turn on the road. And let's assume that the turn is fairly sharp. So you've all have been through that experience, most likely. What do you feel? You feel as if you or your body wants to come out of the car or is pushing against the door of the car. But why is that? The reason is that in the car itself is a accelerating reference frame for your body. And so the force that your body experiences as the car is moving right before it gets into the turn is obviously along a straight line in the direction of motion. As the car starts to turn, your body still wants to move along a straight line. Remember, first law says that in the absence of net force, a body will move on a straight line with constant velocity. So that is your body. And so where is this force coming from that is making you turn? Well, this is the force coming from your contact with the car door. So that force is making you turn. So if that force was not there, you would feel as if there is a force that is making you to go out of the car or fall off the car as the car is taking the turn. This force is actually imaginary. This is only appears to be a force that acts on your body because the car is accelerating reference frame. When the car is moving along a straight line or is moving without any acceleration, then you do not feel a force that is making your body move inside the car in any way, shape, or form. And so this is an example of non-inertial reference frame. A reference frame that accelerates is a non-inertial reference frame. The other type of reference frames are the reference frames that do not accelerate. They are either at rest or they are moving with constant velocity. In those reference frames, there is no imaginary force that acts on an object, and therefore Newton's laws hold perfectly fine. Examples of such reference frames would be a car that is moving with constant velocity on a straight line. The Earth itself is considered to be a inertial reference frame, so reference frame without acceleration. The solar system is another example of inertial reference frame locally for us. The galaxy obviously is another example of inertial reference frame. Now keep in mind that the Earth, because it rotates, it actually is accelerating a little bit. The solar system, because of rotation, also is accelerating a little bit. The galaxy, because of rotation, also is accelerating a little bit. So if we want to be perfectly precise in the definition of a reference frame without acceleration, that would be the universe. The universe does not accelerate. However, for the purposes of our course, considering the Earth to be a reference frame with no acceleration, or in other words, inertial reference frame, is perfectly fine. We are also going to essentially deal with problems only happening, or situations only happening, inside inertial reference frames. So, The term inertial or inertia is very important in understanding Newton's first law. Inertia is a quality of objects that cannot be measured. However, it is related to the mass of objects, and mass is a quantity, physical quantity, that can be measured. So, what is mass? The mass of a body is the characteristic that relates a force on the body to the resulting acceleration. So this statement sort of relates or gives us the relationship between mass, force, and acceleration. Or even more accurately, it states that there is a relationship between mass, force, and acceleration. Mass is simply the amount of material or substance or quote-unquote stuff that is contained in the volume of an object. But the more important property of mass, which is related to inertia, is that mass measures or is a measure of a body's resistance to change in motion, which means change in velocity. How can I illustrate that with a simple example? Think about a shopping cart that is empty. So an empty shopping cart has a very small mass, and from experience you know that an empty shopping cart is very easy to push, pull, or when it's moving already, to turn. Now let's load the shopping cart with some heavy items. You also know from experience that once your shopping cart is full with heavy items, it is much harder to push or pull, and it's also harder to make it turn once it's going on a straight line. So all of this is just because the mass is different. So small mass is easy to manipulate to make it move in a certain way, to accelerate, decelerate, or to change the direction of motion of. And the heavy mass is much harder compared to the lighter mass to accelerate, decelerate, or change the direction of motion of. And so, small mass means small inertia, which means it's easy to make the mass move in a certain way. Large mass means large inertia, which means it's harder to make that mass move in a certain way. And so, going back to the example with you being in a car, as the car takes turn, and you feel as if you want to, come out of the car or get out of the car, or your body wants to get out of the car, this is due to the body's mass and inertia. Your body, because of inertia, doesn't want to change the direction in which it's moving initially before the car enters the turn. So as the car is going around the turn, your body still wants to move along a straight line. And so for you, that feels like as if there is a force that's pushing you out of the car. But this is an imaginary force. This is just the effect of inertia. And this only can be felt when the reference frame is accelerating. So the car is accelerating as it's taking the turn. And so what you're feeling is a force that doesn't really exist. That's why Newton's laws are not valid in non-inertial reference frames. Mass is not the same as weight. This is a common misconception, specifically in the United States, because of the measurement system that's commonly in used here, for which when we are talking about an object and we want to discuss the effects of gravity on it, we talk about the weight of the object. And so very often people misuse the word weight for mass. However, mass and weight, again, are not the same thing, because mass is just the amount of material that is contained in the volume of an object, and weight is the force due to gravity that mass experiences. Finally, mass is inversely proportional to acceleration. So based on those observations, Newton formulated his second law of motion, The second law states that the net force on a body is equal to the product of the body's mass and its acceleration. Since force and acceleration are vector quantities, the relationship stated in the second law is actually a vector equation. So the net force is equal to the mass times the acceleration of the object. As you can see, the net force and the acceleration are proportional to each other. And furthermore, the direction in which those two vectors point is the same. So the net force and the acceleration of motion point in the same direction. Now, since this is a vector equation, in order to actually do calculations with forces and accelerations using second law, we must rewrite this in component form. And so, in general, this is a three-dimensional vector equation, which means that I can write the net force as the sum of its x, y, and z components. And then on the right-hand side, I can write the acceleration as the sum of its x, y, and z components. And then what I get is the x component of the net force is equal to the mass of the moving object times the x component of the acceleration. The y component of the net force is equal to the mass of the moving object times the y component of the acceleration. And the z component of the net force is equal to the mass of the moving object times the z component of the acceleration. Keep in mind that the net force is equal to the sum of all forces that act on the object. So then the x component of the net force will be equal to the sum of x components of all forces that act on the object. The y component of the net force will be equal to the sum of all y components of the forces acting on the object. And finally, the z component of the net force will be equal to the sum of all z components of the forces acting on the object. So the acceleration component along a given axis is caused only by the sum of the force components along the same axis, and not by force components along any other axis. Let's write this out a little bit more in detail to explain how the result in the previous slide was achieved. So first, the net force that acts on the object is just the sum of all forces that act on the object. So then I can rewrite this vector equation as in unit vector notation, in which I have the sum of all x components, I hat, plus the sum of all y components, j hat, plus the sum of all z components, k hat. So now I can just rename the sums in front of each unit vector as just the x, y, and z components of the net force. So I have f net x I hat plus f net y j hat plus f net z k hat. On the other hand, Newton's second law states that the net force is equal to mass times acceleration. However, the acceleration is a three-dimensional vector, so I can also write this as mass times the acceleration presented in unit vector notation. So ax I hat plus ay j hat plus az k hat. And so then I can match the result that I got for the net force here with the right-hand side that I got right here, and I can write that f net x is equal to max, f net y is equal to may, and f net z is equal to maz. And so this now is the second law in component form along each coordinate direction. This representation here allows me to solve problems by separating the components of the vectors that are present in the problem, do the calculations, and then combine the results to get the final answer. When we deal with problems involving forces, we are going to be almost exclusively working in component form, like those, in order to be able to solve our problems. Now, what are the consequences of the second law? If the net force on a body is 0, then the acceleration is 0. That means that the forces that act on the body are all in equilibrium. And just because there is no net force, it doesn't mean that there are no forces acting on the body. It just means that they all cancel each other out and they produce a 0 net force. Another thing to consider is that the acceleration of a body may be 0. However, that doesn't mean that the body is not in motion. It just means that the motion is with constant velocity. So if the acceleration is equal to 0, the velocity is constant. So essentially, the body will be moving along a straight line with constant speed. These are very important considerations that are very useful for solving certain types of problems. Now let's talk a little bit about free body diagrams. So to solve problems with forces or involving forces, we often draw what is known as a free body diagram. So in a free body diagram, the only body that is shown is the one that we are solving for. And then forces are drawn as vector arrows with their tails on the body. We also need to introduce a coordinate system accordingly. For one-dimensional problems, we use a one-dimensional coordinate system. For two-dimensional problems, we use two-dimensional coordinate system. For three-dimensional problems, we use a three-dimensional coordinate system. Acceleration is never a part of a free body diagram. Only forces on a body are present. So when you draw the free body diagram, the only thing that enters that free body diagram is the forces acting on the body. So here we have some examples of a free body diagram depending on the specific situation presented in the problem. So here we have a hockey puck that is sliding across a horizontal surface under the action of this force F1. So I'm introducing a coordinate system which is one-dimensional. I'm going to label the horizontal axis with X, so this is the X-axis. The puck I'm going to represent with a dot, and then the force that acts on the puck starts from the puck and has a direction shown by the arrow. For the next situation, we have again the hockey puck, but this time two forces act on the hockey puck. So I have my coordinate system which is one-dimensional. The hockey puck is this dot. The first force acts to the right, starting from the body. The second force acts to the left, starting from the body. And now in the last situation, I have my hockey puck again, and two forces act on it, F2 and F3. So here is my free body diagram. I have my coordinate system. I have force F2 starting from the body, which is represented with this dot, and the force acts to the left. And then F3 is directed at an angle theta below the x-axis, like shown, starting from the body. And so we will see later with some examples how this idea of a free body diagram is applied to some situations, how the forces are drawn, and what can be derived from that. So sometimes we solve problems that involve a single object and we sometimes also do problems where several objects are involved. And these objects interact only amongst themselves, and they do not interact with the surroundings around them. So when we deal with a situation where we have several objects interacting amongst themselves, we talk about a system of objects. So a system consists of one or more bodies. Any force on the bodies inside a system exerted by bodies outside of the system is an external force. The net force acting on a system is equal to the sum of all external forces acting on the system. Forces exerted between bodies in a system are called internal forces. When we are drawing a free body diagram, the internal forces are not included in the drawing, because the internal forces do not cause the system to accelerate. These are forces that arise only from the interaction of the objects within the system. So these forces are not part of the external force, and the external force is the only force that causes the system to accelerate. Now, when you're drawing free body diagrams, there is a difference between the free body diagram for the entire system and the free body diagram for the individual members of the system. When you're drawing the individual members of the system, in a free body diagram, you would draw all the forces that apply or act on each member. When you're drawing the free body diagram of the entire system, you are going to only draw the external forces that act on the system. Now let's talk about some particular forces. The first force that I will discuss is the gravitational force. The gravitational force is a pull that acts on a body, and it is directed towards a second body. So generally, we consider situations where the second body is the Earth. Most of the examples that we are going to deal with are related to the gravity of Earth. So, in a free fall, with no drag from the air, the gravitational force, Fg, comes in with a minus sign. Since the positive y orientation we always consider to be vertically up. And from Newton's second law, the gravitational force will be equal to the product of mass and acceleration, which is the gravitational acceleration, which comes in with the minus sign because, again, it's directed opposite to what we consider positive vertical orientation. And so the two minuses here will cancel out, and finally we get that the gravitational force Fg is simply equal to mass times gravitational acceleration. Now we are ready to define what weight is. So weight is the name given to the gravitational force that one body, such as the Earth, exerts on another body, such as a satellite, a car, a box, a ball that's dropped from a waist height, or any other body that is close to Earth's surface. Weight being a force means that it's measured in newtons, and by the nature of how gravity works, we know that weight is always directed downwards towards the center of the Earth. And so the weight, W, is equal to the gravitational force that an object experiences due to the gravity of Earth. The weight, W, of a body is equal to the magnitude Fg of the gravitational force that's acting on the body. How do we measure the weight of an object? Well, one could use a balance to compare a body to known masses. Find its mass and compare the weight. One could use a spring scale that measures the weight on a calibrated scale. much like bathroom scales. As I said before, weight is not the same as mass. Mass is just the amount of material in the volume of an object, while weight is the force that acts on that mass due to gravity. To calculate the weight, we must include the gravitational acceleration value g, which varies from place to place. For example, the gravitational acceleration on Earth is different than the gravitational acceleration on the Moon. So an object with the same mass on Earth and the Moon, remember mass doesn't change because it's the amount of material inside the volume of an object, will have different weight on Earth and the Moon. And this is because weight is a vector quantity. It can change, while mass is a constant and cannot change. Weight must be measured, and this is very important, weight must be measured when the body is not accelerating vertically. Remember, Newton's laws do not apply for reference frames that are accelerating. So, if you measure the weight of an object in a reference frame that is accelerating vertically, you're not going to get the correct measurement for that weight. Keep in mind that if the reference frame is accelerating horizontally, you can measure the weight accurately. But, again, if the reference frame is accelerating vertically, you cannot measure the weight accurately. I will give you an example of how the vertical acceleration changes the reading of the scales which are used to measure the weight after we talk about one other force that always appears when the weight of an object is a factor. That other force is the normal force. So if you're standing on a surface, you are applying your weight down on that surface. So for example, here we have a block that is resting on a table, and so the block is pushing down with its weight, or the force due to gravity. Well, the surface, right here, pushes back on the block. Or if you're standing on a surface, the surface pushes back on you with what is known as the normal force. So the normal force, Fn, is always present when an object applies its weight or pushes down with its weight on another surface. The normal force is always perpendicular to the interface between the two objects in contact. So here, the block is resting on a horizontal table surface, so the normal force is perpendicular to that table surface. If you had an incline and the block was resting on the incline, then the normal force will be perpendicular to the incline, like so. So again, the normal force is always perpendicular to the first surface on which the object is resting. So here we have the table, here we have some incline. This is very important. And so, if I drew the free body diagram of this example here, this is my block. The force of gravity is down, the normal force is up. And now, since this is a vertical problem, I need to introduce a vertical coordinate direction. So then, in this example, we have the block resting on the flat surface. The weight, or force which is equal to the force of gravity, pushes down on the surface. The surface responds with the normal force pushing straight up. And so I can then say that the normal force is equal to the force of gravity, and this of course is by magnitude. Or in other words, the normal force is equal to m times g. And this is a situation where there is no vertical acceleration. Let's see what happens if there is vertical acceleration. What you do is you take bathroom scales and you place them inside an elevator. So here is the elevator, bathroom scales, a person is standing on the bathroom scales, the elevator is moving up with some acceleration A. So the scales will measure the weight of the person, Fg, and actually the scales will feel the force of weight of the person, and so the spring inside will basically react with the normal force that the scales will measure. So let's see what this normal force is equal to. And let's compare that with the previous result when there was no vertical acceleration. In order to find the normal force, I must apply Newton's second law. Newton's second law simply stated that the net force is equal to mass times acceleration. Here the motion is in vertical direction only, in y direction, so therefore my net force, the second law in component form will simply look like the y component of the net force is equal to mass times the acceleration in y direction, and this I can call AY here. So then what is the net force in y direction? Well, the net force in y direction will simply be the normal force minus the gravitational force. Those are the only two forces that act in y direction, and so the normal force points in positive direction, the gravitational force points in negative direction, so we have normal force minus gravitational force, accounting for the direction in which the forces point. So then from here we get that the net force in y direction is simply equal to the normal force minus mg. And then on the other hand, this will be equal to mass times the y component of the acceleration, so that would be equal to may. Well, from here I can solve for the normal force. And so finally the normal force is equal to m times ay plus g. So this result here tells me that the scales which read that normal force or show us the normal force will read force that is larger than the actual weight of the person. The weight of the person is simply mass times gravitational acceleration, but here we have another term that's added, that is the value of the vertical acceleration of the elevator. So, if the elevator is moving vertically up with some acceleration, the reading on the scales will be different than the reading when the scales aren't accelerating vertically. The reading here will be wrong. What this reading is called apparent weight. Let's see what happens when the elevator is moving down with acceleration ay. Here is the elevator, the bathroom scales inside, a person is standing on the bathroom scales, the person pushes down on the scales with their weight, m times g, and as a result the scales respond with the normal force Fn. So let's find what this force Fn is equal to. And again, let's compare to the first result and then to the second result. Again, to solve the problem, I will apply Newton's second law in component form. So essentially, I must find the net force in y direction and make it equal to mass times the acceleration in y direction. What is the net force equal to here? The net force here is equal exactly to the same net force in the previous example. That will be the normal force minus the weight of the person. So the net force in y direction is equal to the normal force minus mass times gravitational acceleration. On the other hand, that is also equal to mass times acceleration in y direction. And so this means that that's equal to mass times minus AY. Why do I have a minus sign in front of AY this time? Because the direction of AY is opposite to my positive Y direction. Okay, so now solving for the normal force, I get that Fn is equal to mg minus AY. So the normal force now is different than the normal force before when the elevator was accelerating up, and it's again different than the normal force when there is no vertical acceleration. This time the acceleration of motion is less than the gravitational acceleration. So here the acceleration was more than the gravitational acceleration, here it's less than the gravitational acceleration. So what does that mean? So in the first case, when the elevator is going up with acceleration, the reading of the scales will be more than the actual weight of the person. In the second case, when the elevator is going down with acceleration, the reading of the scales will be less than the actual weight of the person. So this also, of course, is known as apparent weight. How can you sort of visualize what is happening here? Well, I hope you have been in a fast-moving elevator, and you know that when the elevator is moving up, you feel as if you're getting a little bit heavier. You also know that when the elevator is moving down, you feel a little bit lighter. The same effect is achieved on a Ferris wheel. As you're going up or climbing up the Ferris wheel, you feel as if you feel a little bit heavier. As you start going down, you feel a little bit lighter. All of that is caused by the directions of your weight, the normal force, and the vertical acceleration of motion. As you can see, in the first example here, we have an inertial reference frame that does not accelerate. In the other two examples, we have non-inertial reference frames. Those are reference frames that move with acceleration. And so in those situations, as you can see, Newton's second law does not apply. So this is a very good illustration of that idea. Another very specific force, which is also one of the most dominant and present forces in the universe, is the force of friction, or just friction. The force of friction occurs when the object slides or attempts to slide over another object. The force of friction is directed along the contact surface opposite to the direction of intended motion. And so here is a simple example of a block that is sliding on top of a flat surface, horizontal surface as well. The direction of attempted slide is to the right. Then the force of friction arises at the interface between the two surfaces in direction opposite to the direction of attempted motion. We're going to learn more about the force of friction and how to calculate it in the next lecture. Another very common force is the tension force. A cord or a rope or a chain or a cable is attached to a body and pulled taut. This cord will pull on the body with force T, which is directed along the cord. When that happens, we say that the cord is under tension. We label the force of tension with capital T. We are going to consider only massless and unstretchable cords when we are dealing with problems involving tension. However, this is, of course, an idealized model of a cord. We know that cords have mass. We know that cords may stretch depending on the material from which they're made. And we also know that they do not necessarily have a uniform mass distribution, which means that the tension along a cord may vary depending on where, how long the cord is and where the forces are acting exactly. But again, for our particular purposes, we are going to use idealized notion for cords, so we are going to consider them to be massless, to be unstretchable, and to be uniform. When we deal with cords running over pulleys, for now, we are going to also consider the pulleys to be massless and frictionless. So here are some examples of situations where the force of tension arises. So we have an object to which a cord or a rope or a string or a cable is attached. And so if we pull on one end of the cable, a force of tension arises, which is balanced by a force of tension applied on the other end of the rope, which is attached to the object. So there is a balance here between the two forces. There is no stretching of the cable, there is no pulling or anything like that. Now, in problems that we are solving, we are always going to only, when we do the free body diagram, indicate the force of tension that acts on the object itself. We are never going to show the other force of tension. Here is another example of a problem where the force of tension arises. So we have the cable here running over a pulley. If we are pulling on this end of the cable, a force of tension straight up arises. And then on the other end of the cable, which is attached to the body, a force of tension arises in that direction. And the last example is an object attached to a cable that runs over a vertical pulley like that. If we pull down on the free end of the cable, the force of tension that arises points straight up. On the other side, the object is essentially pulling on this cable with its force of weight straight down, so a force of tension arises here that is directed along the cable. Since the cable here is perfect, uniform, doesn't stretch, it's massless, the two forces of tension are in general equal. We will see some situations, however, where the forces of tension are not the same. We will examine some problems involving that notion. We'll see how that works. Now we are ready to talk about Newton's third law. So objects interact by the application of forces. So since forces are push or a pull, that means that objects interact through push or pull, or they push on or pull on each other. So Newton's third law, which is known as the law of action and reaction, says that when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. And so the simplest example that I can give you is an object, a block, that is resting on a surface. We talked about that already. We know that the block is going to push down on the surface with its weight. We also know that the surface is going to respond with normal force. Well, this is an example of the application of Newton's third law. So two bodies interact, so that's the block and the surface, and they exert forces on each other. The block pushes down on the surface with the force of weight. The surface pushes up on the block with the normal force. So let's rename these forces that are listed right here in terms of the example that I gave. FBC, that would be the force of gravity. So that is m times g. FCB, that's going to be the normal force with which the surface acts on the block. And so by magnitude, the two forces are equal to each other. As vectors, the two forces are opposite to each other. So the force of gravity is equal to minus the normal force as vectors. But again, by magnitude, they are equal to each other. So the pair of forces that arise from the interaction of two objects is oftentimes called the third law force pair, or simply action-reaction pair. And so anytime any two objects interact with each other, there is a third law force pair or action-reaction pair. So here we have a few other examples. We have a cantaloupe resting on a table surface. And so there is an action-reaction pair arising between the cantaloupe and the surface. The cantaloupe pushes down on the surface with its gravitational force. The table reacts with the normal force. So that is an action-reaction pair between the cantaloupe and the table. Let's draw these forces on the actual drawing. So here we have the force of the cantaloupe on the table, which is the gravitational force with which the Earth pulls on the cantaloupe. And then as a result, the cantaloupe reacts back with the normal force, which we'll call FCT. Now, there is another set of action-reaction forces that are present in this configuration here, and that is the pair forces due to the interaction between the cantaloupe and the Earth. So the Earth pulls on the cantaloupe with the gravitational force FCE. However, the cantaloupe pulls on the Earth with its own gravitational force FEC, and of course the two gravitational forces are equal to each other. Now, why don't we see the Earth move towards the cantaloupe? Well, this gravitational force is extremely small, and also the Earth is extremely big and heavy, and therefore it barely really moves due to that force. So this is an example of action-reaction pair of forces. A similar example is when we have the gravitational interaction between the Earth and the Moon. The gravitational interaction between the Earth and the Moon is actually better study of the fact that there is a gravitational force that the Moon applies on the Earth. Why is that? Well, we know that the oceans experience ebbs and tides, and so when the tides happen, that is because the gravity of the Moon pulls on the Earth, and of course the water is much easier to move than the entire Earth. Another thing that is a consequence of the gravitational interaction between the Moon and the Earth is that both celestial bodies essentially circle around a common center of gravity, which is not at the center of Earth, but is shifted a little bit. I believe about 60 or so kilometers from the center of Earth. So the Earth essentially orbits around that, and then the Moon also orbits around that. So the system of two celestial bodies orbits around this common center of mass, and that is due to the fact that there is gravitational interaction between the two. Now let's do a few example problems to illustrate how Newton's laws are applied and how to use free body diagrams to sketch the forces that act on various bodies and problems. We have a system of two blocks, block number 1 and block number 2, that are connected with a cable that runs over a pulley. Block number 1 slides across a horizontal surface without friction, and block number 2 is hanging on the cable. The question is to find an expression for the acceleration of the system and an expression for the tension in the cable or in the rope. In order to be able to solve the problem, I need to draw a free body diagram. I'm going to draw the free body diagram for both blocks at the same time. So for block number 1, we have the weight of the block straight down. That will be equal to m times g. We have the normal force due to the surface, Fn straight up. We also have the tension in the cable. And those are all forces that act on this block. For block number 2, we have the weight of the block straight down. the weight of the block straight down, so this will be m times g. And then we have the tension in the rope straight up, like so. And those are the only two forces that act on the system. Since the two blocks are connected together with this cable, and the cable, again, we consider to be not stretchable, uniform, massless, that means that both blocks will be moving with the same acceleration. So this is my system of two objects that is moving with the same acceleration. So that means that I can apply Newton's second law for each object in the system separately, and then solve this system of two equations, the second law for block number 1 and the second law for block number 2, and from that I can find the expressions for the acceleration and then for the tension in the cable. So before I start solving the problem, I also need, of course, to introduce a coordinate system. The way I will select my coordinate system will be vertical axis straight up is the y-axis, and then positive horizontal axis x is to the right. So positive vertical axis is up, positive horizontal axis is right. Now for block number 1, we have net forces in both x direction and y direction. So that means that Newton's second law here will be written for both coordinate directions. So for the x coordinate direction, the net force in x direction is equal to the force of tension. That is the only force that acts on this block. And of course, from Newton's second law, that is also equal to the mass of this block times the acceleration of motion. Now, for the vertical direction, the net force in y direction is simply equal to Fn minus mg, so the normal force minus the weight of the block. Vertically, the block does not accelerate. There is no vertical motion at all. So that means that this net force is equal to 0. Now let's write Newton's second law for block number 2. So for block number 2, we only have vertical motion. Therefore, the net force in x direction is equal to 0. And so the net force in y direction is simply given by T minus mg. And this will be equal to the mass of the block times the acceleration of motion. Now, looking at those equations, you can see that I have an actual expression here for the force of tension from the x component of the net force for block 1. So right here. So I can take that and plug it in the y component of the net force for block number 2, right there. And then I can find an expression for the acceleration A. Let's do that. Before I start solving the problem for the acceleration, one more very important thing to note is that the acceleration of block number 2, is accelerating down, so that's the direction of the acceleration for block number 2. Well, this is in direction opposite to the positive y direction. So therefore, right here in this equation, I must introduce a minus sign in order to account for that direction. If this minus sign is forgotten, then the answer that you will get for the acceleration will be wrong. And so first we get, when I substitute MA for block number 1 in here, we have mm minus mg is equal to negative ma for the small block. From here we get that the mass of the big block plus the mass of the small block times the acceleration of the system is equal to the mass of the small block times gravitational acceleration, that is the weight of the small block. And now I can solve for the acceleration. From here, the acceleration of the system A is equal to the weight of the small block divided by the total mass of the system. And so this is a universal expression for that type of problem, which can find me the acceleration of a system of two blocks as long as I know the mass of the blocks. On another note, this is the principle of operation of a device that is known as outward machine, which consists of a pulley and two masses connected with a cable or a rope or a string. And this device can be used to actually measure the acceleration of motion of the system. Now that I have an expression for the acceleration A, I can go back into the x component of the net force equation for block number 1 to find an expression for the tension in the cable. And the expression for the tension force in the cable looks like so. The mass of block number 1 times the mass of block number 2 times gravitational acceleration divided by the total mass of the system. Now let's see what we get for the tension and the acceleration using the numbers provided in the problem. For the acceleration, we get 3.8 meters per second squared, and for the tension, we get 13 newtons. Now let's do one more conceptual example. Here is a block that's being pulled up a ramp. And the ramp will have an angle with the horizontal, let's call it theta. And so the force that acts on this, or the pulling force that is applied on the cable that's pulling the block, let's call it T. The question is, what's the acceleration with which this block is moving? And let's see what other kind of information can we get from this particular configuration. So first, let's introduce a coordinate system in which we're going to draw the free body diagram for this problem. Now I'm going to select my coordinate system so that the positive vertical direction is perpendicular to the incline, and then the positive x direction is parallel to the incline pointing up the incline. Let's draw the forces that act on this block. So I already drew the tension force this way. Now the weight of the block is straight down towards the ground. And then, of course, there is the normal force with which the surface of the incline responds to the block. And the normal force is always perpendicular to that surface, so the normal force is directed like so. Now, notice that the weight of the block is not parallel to the y-axis. It makes an angle with the y-axis. So that means that the weight has to be resolved into a y and an x component in order to be able to write expressions for the net force in x and y direction for the block. And so here is one of the components. So that is the y component of the weight. I call it the y component because it's parallel to the y-axis. And here is the x component. And again, it is the x component because it's parallel to the x-axis. So the block is under the action of the tension force and the x component of the weight of the block. This is along the x-axis. So those two forces will add up to give us the net force x component. and then the y component of the weight and the normal force combine to give us the net force y component that acts on the block. Now, since I want to find the x and y components of the weight, I need to know an angle here in this triangle. This triangle is formed essentially by the weight, the x component, and the y component. Okay, so if you look at the incline and the ground, this forms a right triangle. And this right triangle is similar to that right triangle. Like if you take the small triangle and flip it and rotate, you will find out that the weight, that vector, matches the hypotenuse of the incline. The y component is the base, and then the x component is the height. And so that means that this angle here between the weight and the y component of the weight is the same as that angle theta. Well, now I can express the component of the weight with a trig function and the weight itself. So let's do that. So wx is equal to w sine of theta, or in other words, mg sine of theta. And wy is equal to w cosine of theta, or this is mg cosine of theta. Okay, now I'm ready to write Newton's second law for the x and y directions. So the net force in x direction is going to be the tension minus the x component of the weight. Again, the tension points in positive x direction, therefore I take it with a plus sign. The x component of the weight points in negative x direction, therefore I take it with a negative sign. And so this will be equal to tension minus mg sine of theta. I took that from here. And on another hand, this is equal to the mass of the block times the acceleration of the block. And let's call this one AX. Okay, now the net force in y direction. F net in y direction is simply equal to the normal force minus the y component of the weight. Again, the normal force is taken with a positive sign because it points in positive y direction. The y component of the weight is taken with the negative sign because it points in negative y direction. And so this is equal to the normal force minus mg cosine of theta, and this is equal to 0 because there is no motion in vertical direction. There is no acceleration. So from here I can write expressions for the force of tension. So the tension is simply equal to max divided by mg sine of theta. So if I know the acceleration ax, I could calculate the tension. Similarly, I can also calculate the acceleration if I knew the tension. I just need to rearrange the terms in that relationship. From the y component of the net force, I can also figure out what the normal force that acts on the block. So the normal force is equal to simply mg cosine of theta, or that is the y component of the weight. So from here, of course, variations of this problem can be encountered. For example, the tension force might be applied at an angle, so not parallel to the incline, but at some angle from the incline, like so or like so, which then will introduce components of the tension force along each coordinate direction, which then is going to just require to add or modify the equations for the net force in x and y direction. And that, of course, will change slightly the look of the expressions for the tension, for the normal force, and and for the acceleration. Now, if you wanted to find the acceleration and tension force if you didn't know either of the two, that would require that there is a second block connected to the rope here, similar to the previous example. So the rope will be running over a pulley, and the second block will be moving vertically up or down, in which case you can then calculate the tension and the acceleration by solving a system of equations again. So we are going to see several problems during work we do on this chapter that will be involving inclines, and you will see how these equations will develop there to solve those problems. In the next chapter, we are going to also include the force of friction in similar situations and the previous example as well. And so that will simply modify the equations by adding an extra term. However, conceptually, it's not going to change the method of solving those types of problems. So here I'm going to stop with the lecture. And we are going to do several different types of problems in class to practice more the application of Newton's law in solving various problems involving forces.